Last time I talked about the black box model, which completely relies upon a computer, numbers in, numbers out. At the end, you have a model that takes a very complicated, uninterpretable form that you can't really do much with. The other extreme was the white box model, which is pure physics, chemistry, and biology. It does not use a machine at all. It comes from first principles. You have a governing equation, and you have a model. Now, that model, while it's ideal and in principle sounds great, it's oftentimes impractical and not very useful because you can't have a closed, nice set of equations you can solve. Now, I introduced last time this gray box model, which incorporates elements of both. I'm going to take structure and physics that I know, incorporate that into my model, and the terms that I can't figure out, which is really hard for a human to figure out, I'm going to rely upon a computer to do that for me, given data. Now, what's really nice about the gray box model, and the reason why it's called the gray box model, is that the grayness can be slid between the fully white box model and the fully black box model. Now, what I'm going to talk to you about today, I think a lot of people would consider to be very, very close to the white box model because we're going to use a lot of physical insight and a lot of mathematical structure to constrain the problem to a very, very, very small search space. But if you want to relax that assumption and relax that structure and take away that structure away from how I'm going to solve it, you can always do that. You'll just slide that gray box model closer and closer over more similar to a black box model. So the scientist and engineer, it really comes down to where you put your structure and how you set up the architecture of your problem. And I think this is where most of the creativity comes in solving research and science engineering problems related to these sorts of measurements and how you develop a model. Where do you put that slider across from pure physics, chemistry, biology, all the way to pure computer and machine language? So let's get started with the gray box model. Now, the physical intuition that we have using your knowledge of physics is that we can take functions and expand them in Fourier sines and cosines. We've spent a lot of time doing that. I cover a big chunk of my lectures in applied mathematics on Fourier series and how powerful of an idea it is that you can take the world and break it down into a sum of a bunch of sines and cosines, and you can reconstruct functions from the ground up. So we can apply that principle for our unknown function. We can say, or make a guess, that our unknown function fx comma t can be expanded as a orthogonal basis function. So we can model our unknown forcing function as a Fourier series, also called an orthogonal basis function, using sines in this particular case. So usually we write n pi x over L. In this particular case, L is 1, and therefore we have sine n pi x. So we're going to add up a bunch of sine with different frequencies to build up our mystery unknown function f, the forcing function, the heat generation inside our material. That's a guess that we're making. Okay, so the coefficients are usually found using orthogonality, and I spent a lot of time talking about how you can find the weights a sub n to model a function. And in my classes, I usually cover it in the case where this function f is only a function of a single independent variable x, but in general, it could be a multivariable function. In that case, we're expanding in a orthogonal basis series for only the space part of the problem. So f is a function of position and time. The position, the space part, is modeled as a Fourier series, and the coefficients are going to be a function of time now. And the coefficients, which usually are a fixed value, a constant value that models some function using a bunch of sines and cosines, the coefficients are time varying. So if your function is time varying in time, if your coefficients are tracking that time variation, that will just show up here. No big deal. I think a lot of you can picture that. If you know the Fourier series, you can kind of imagine that, yeah, if my coefficients, my weights of each of those frequencies are also time varying, I might be able to capture the full function. Okay, so the weights are going to be a function of time. So if you think about it, we know the position x. We can, for a given x, if you tell me an x, I can evaluate sine n pi x. You're going to sum up all of those indices from n going from 0 to infinity. So you know this part, but you don't know the coefficients. So you don't know the weights as a function of time t. So we know the space part of this mystery function now, but we don't know the time dependence. We're shoving all of the unknown of this term into the weights a sub n. So if we can somehow use data to figure out what these coefficients a sub n are and how they vary with time, then we're good to go, because we can take this function here, plug it into this equation, and solve it. In fact, let's solve it using a technique that you guys are all very familiar with, using separation of variables. Now, if you make this model of your forcing function f(x, t), you can actually make a lot of progress analytically, pen and paper, in solving this equation using separation of variables. Nothing new from what you already know how to do. So let's just try it. Let's try separation of variables. All right, separation of variables. I'm going to express my full temperature profile as some function of position and time, break it down into a product of theta, which only depends on time t, times capital X, which is a function that only depends on position x. So we're separating the two independent variables as a product of some function of time, some function of position x. Now, I've done this separation of variables many, many times in my past lectures, so please, again, watch that if you're unfamiliar with this procedure. What you get is you plug this equation into your partial differential equation. You separate all the functions of time onto one side of the equation, all the functions of position onto the other side of the equation. The only way to make that equal is if they're both equal to a constant. So now you have two separate ODEs to solve. And you already know from your experience that for this boundary condition of temperature equal to 0 on both sides, homogeneous Dirichlet boundary conditions, you're going to get the sine series to come out for your ODE for x. So the solution for the capital X function is just going to be a summation of a bunch of sines with eigenvalues equal to n pi. Okay, let's write all that down. So at the end of that procedure, you would end up with a form that looks something like this. So once you solve your x ODE, you're going to find that it's going to be sine n pi x. And you're going to multiply that with the function of t, which for a usual heat equation problem without the forcing term would just be exponential of negative thermal diffusivity times the eigenvalues squared times time, which is the exponential decay, with some prefactor out in front from which you use an initial condition to solve the problem. But in this case, things are a little bit different, right? We have this unknown forcing term. So let's plug this form back into our full PDE and see what we get. All right, so what I've done here is to take this form right here on the bottom, plug this into our differential equation. So the first term on the left, the accumulation term, the sign's going to pass right through. We're just going to have a first derivative of theta n of t. There it is, d theta dt. That's the accumulation term. Now, the diffusion term, we're going to take the space derivative of this function, and therefore the theta of t will just pop right outside. We get two derivatives in position, so we get n pi squared to pop out. And after that, you're going to get a negative sign, so you're going to get a negative sign out here. And therefore, we move it over to the left-hand side. This is going to turn into a positive sign. Lastly, we have this forcing function f(x, t), which we've now expanded in a Fourier series. So we're going to plug in f into here. We're going to have a summation n going from 0 to infinity, a sub n of t, which is our unknown. We don't know what a sub n t is. We know the space part though, so we're going to plug it into here, and that's this term right here, a sub n t sine n pi x. This right here is exactly what we have in the forcing function. And what I've done here is just skipped one step. I've factored out the summation and the sine n pi x. I hope you can see that if I were to multiply the sine n pi x into each term, you'd exactly get back what each of the terms are if I were to just simply plug it in. Okay, so we get this equation. This says that everything on the left-hand side must be equal to 0 for all x and time. The only possible way this would ever be true is if the stuff inside the bracket is equal to 0, right? So we conclude that this thing must be equal to 0. But if this thing is equal to 0, all we have is a first-order ODE for our function theta. Let's write that down. We get an ODE that looks something like this. Once again, this a sub n of t came from our model for our forcing function, but we don't know what this is. So that's an unknown term. But from the perspective of this ODE, it's a forcing function, right? This is the non-homogeneous term. When we solve first-order ODEs, we have the homogeneous part and the non-homogeneous part. This non-homogeneous part is going to produce a particular solution. Homogeneous solution, particular solution. Therefore, our forcing over here just becomes a non-homogeneous term for the ODE for one part of the separation of variables. No big deal, because you can solve this equation very easily. This is, in fact, probably the very first differential equation you ever solved in your life. This is just a first-order ODE, linear, and it's non-homogeneous. So we could just use the integration factor. Let's just write the solution down. You'd get a solution that looks something like this. Theta, as some function of time t, has an exponential term, negative alpha pi n squared times time t, integral from lower bound time t equals 0, upper bound time t, which is corresponding to this time at a particular point in time, is equal to the integrand, which is a sub n of tau, which we don't know, that's an unknown. Okay, whatever that thing is, it's the coefficient of the Fourier series that depends on time, times exponential of alpha n pi squared times tau integrated over d tau. If you're wondering why I swapped from t to tau, because now we have a dummy variable tau inside of here. We're integrating over the variable tau, and we're integrating from 0 to time t up here. And I don't want to use time inside of here, because if I had used t, and little t down here, I'm integrating from 0 to t, and it gets confusing. So now I'm using a dummy variable, tau, that runs across my integral for d tau. This is just straightforward integration factor. Nothing fancy at all. You should all be able to do this just very quickly. Now what we have is our full solution because we solved for our coefficients, which are now a function of time. I can stick it into this overall temperature profile, and we have our final solution. Let's write that down. All right, now we have our final solution for the temperature as a function of position and time is equal to this thing right here, a sum coming from the sum over here from the Fourier series, sine n pi x over at the tail end, and then everything inside of here is this integral, which is the solution for theta. That's the time-dependent part of our separation of variables solution. So all I've done is a small little algebra step where I've taken my exponential term prefactor out in front and then put it inside this exponential inside this integrand. Okay, that's just for compactness. Again, you can see that we're integrating over tau. I've just put a t inside. So this is negative t, and then I have a plus tau up here. So negative, negative, and it becomes tau. Okay, that's just the same expressions. I just put it in for compactness. Now, if we know a sub n, which is a function of t, then we're done. Once we know a, the weights of the forcing function, then we can actually integrate this. That's the only thing we don't know. The model is complete except for the coefficients. Once we know the coefficients and its variation with time, we can just integrate this because this is just an integral. And then we're done. We have a model for our temperature profile as a particular point in space and in time. And now we're going to use a computer and data we've collected over the temperature profile to learn what these coefficients are. But before that, this general procedure that I've just shown you here, by assuming a basis function for a forcing term, expanding in terms of sines and cosines, and going through here and getting an ODE for your weights, this general strategy is called spectral method. It's very commonly used in science and engineering. Spectral method. It's a very powerful technique based upon Fourier series that helps you solve PDEs in very complex equations. Now, I'm going to erase some of these unnecessary notes and just circle this main equation so that we can focus on one equation. All right, so this is our final gray box model. We've incorporated a lot of physical insights. And we're down to one thing that we don't know, a sub n as some function of time t. Now, here's where we're going to rely upon the help of ML. So we're going to use data to figure out what this coefficient is. And once we figure that out, we have our model. For a particular time and position, we have a prediction of the temperature inside our material. So let's write down the architecture of what we just did in this gray box model. All right, there's been a lot of math going on, and I think we might be just buried inside the details. Let's back up a little bit and look at the architecture of how we designed this gray box model. First, we have position and time as our input. That's going to go through a neural network that will output not the full temperature, but instead a coefficient, a vector of coefficients, a sub n, which will be a function of time t. And it's going to have a1, which corresponds to this coefficient for sine 1 pi x. So once we have a sub 1 of time, we have sine 1 pi x. Great, we found that coefficient and its variation with time. Sine 2 pi x will correspond to a sub 2 time of t, and so on. A3 would correspond to sine 3 pi x, and so on. So for the particular example I'm going to show you on MATLAB, I'm just going to go to 5 modes. So we're going to have sine 1, 2, 3, 4, 5, sine 5 pi x, and each of their coefficients. So position and time goes in. We have, in this case, 5 outputs coming out from the neural network corresponding to the 5 modes. The coefficients from sine 1 to sine 5. We get the a sub n. Once we have that, we're game, because we can plug in a1 through a5 into this term right here and just numerically integrate this expression using the trapezoid rule, which you also learned. The area under a curve is just trapezoid. Once we have the value of a as a function of tau, then this is the structured model that I circled in pink that will come in, mix with the a's, and then boom, out comes my full temperature profile because I have it right here. That is my model. That is a model that I'm going to go from this end, position and time, boom, all the way out to the temperature, which was our goal to begin with. Now, there's going to be a training process involved because early on, this neural network, early in training, is going to be very poor. So it's going to spit out a very, very incorrect version of A1, A2, A3, A4, and A5. Therefore, at the very end, we need to minimize and iterate to fix this so that the neural network converges to the more close solution for a sub n. So we're going to complete the training loop by taking our intermediate solution for t, which is going to be our model temperature profile, compare it with the true value. T true is your data, the experimental data you collected of the temperature profile in your material. We're going to harmonically penalize that. So we're going to take your actual temperature value, subtract it from the true value, square it, try to minimize this error. This is called the loss. And we're going to try to drive that loss down to 0. And if it's not 0, we're going to go back up, readjust the parameters inside this neural network that will take in space and time and input new set of Fourier coefficients, get my temperature, combined with a structured model, boom, minimize, over and over and over again. So you're going to do this loop many, 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 many times, and that's the training process. So this loop that I showed in blue, that's the actual training. So I hope you can see the picture. This is a physics-informed or gray box model where we've put a lot of mathematical structure based upon our knowledge of the heat equation. We know how to use separation of variables, but there's a term in there that's really hard to solve. No problem. just rely upon the computer to help us out, figure out what those coefficients are. Boom, we have our final solution. We can train that using our real experimental data and then go over and over and over. Now, this is all predicated on the assumption and the guess that whatever material you have follows this governing equation. That may or may not be true. This thermal diffusivity may not be a constant. It may vary as a function of position. It might depend on the temperature T, right? So if your model here is wrong, you're kind of forcing your architecture to learn in a space that's kind of wrong. And so it's going to compensate for that of model inaccuracies by figuring out a new set of parameters that will adjust for your wrong assumptions that you put in. Now, this is where it gets really tricky. And this is where you have to shine in your creativity as a scientist and engineer. Where do you constrain? Where do you let free? Here we constrained our solution to evolve from this differential equation. This model already has a lot of physical approximations built into it. We're saying that this is a solution to the heat equation. We're ignoring the variations in the thermal diffusivity. We're ignoring the fact that this unknown could be something more complicated than a bunch of sines and cosines. But this is where you have to think about how much structure you put in and where do you leave your unknowns. If you feel uncomfortable with putting this much structure and asserting this much physics into the problem, no big deal. Just back off of it. Just remove physics from your model and you can still have a structure like this, but you'll have more unknowns. You'll have more degrees of freedom. What you've done there is just expanded the circle by which the computer will help you out more. So it's a trade-off between how much human intervention you put in and how much AI or computer intervention you put in. It's the combination of both that will produce the best possible model. Okay, let's graphically illustrate what I just said. So earlier, I showed you an example that ignores all the physics and uses a black box model. Inputs position and time in, neural network learns everything and gives you out temperature. So what you are doing is effectively saying, I want to learn out of the entire universe of coupling between position and time to temperature, and I want you to learn from the entire universe the dependencies. So it's saying, in this black box model, I want you to search in the entire universe the best optimal relationship between position, time, and temperature. A list of numbers to another list of numbers. When you're doing this gray box model, by putting in so much mathematical structure and physics into the problem, you're asking this neural network to do not a search over this entire universe, but it's saying only learn a part and search in a part of this universe. So with the gray box, this whole structure that you've put in is designed so that the neural network only learns in this small little space inside the all possibility of combinations. It's searching and learning only this small little part. So morally, what you've done is you've taken this entire universe of combinations where the machine has to search over the parameters to a much narrower one, like that, by using your human intelligence. So this is where physics come into place. So physics can help shrink your search space from the entire universe to a small little crop. Of course, what that does is it puts less strain on the computer to search within that space, but it also comes with some dangers. Suppose your actual solution, whatever the dependence is out here. If your actual dependence in the parameter space and the actual solution lies out here, the dependence lies out here, then you've inadvertently constrained the entire possibility to a search space that's different from the actual true model where it lies. So in that case, what you've done is to force your model to look for a space where there's no answer. So again, this is the trade-off between you as a scientist and engineer. You have to think about where you want to put the structure. How much physics do you want to put in? How much do you want to relax by? And this is the trade-off. This is an extremely active and current area of research. This trade-off between how much structure, how much machine do you put in? Okay, so now enough with the theory. Let me show you some examples where I use this gray box for a few specific simulated data sets for different functions of f. The first case we'll consider is a simulated data set that was produced using this forcing function. Cosine of 2 pi t times sine pi x. This is the exact same forcing function I showed you for the black box example, where we use this to generate our solution by solving this partial differential equation, creating a list of numbers for a temperature profile, and we use the black box model to develop a model between position and temperature. Same model applied now to the gray box case. We're going to use this, find our solution, but we're not going to assume that we know the solution at the very end. All we're going to use is data on the temperature to train our neural network, combine with our structured model, and see what our final answer looks like. Let's go over to the screen. I want to first explain this model to you in code and show you how I implement all this structured physics-informed model into code. So here is the physics-constrained or gray box model code, where first I'm loading this case 1 of single mode, which is cosine of 2 pi t times sine pi x. This data matrix contains the position, time, and all the temperature measurements, right? The simulated data set. So I'm extracting out those positions, times, the thermal diffusivity that I inputted, which is 0.01, and then the true temperature profile. That's your data, right? That's your T true. This is the final T true data. Over here in the minimization, you're minimizing your model T that you're training from the actual true temperature profile. That's contained in this data set right here. Okay. So, like I said earlier, in this structured gray box model, we need to specify the number of modes because, like I said, we're expressing this basis function and this final temperature profile as a bunch of summations of signs. So we need to have an upper bound. Practically, we can't go out to infinity. So I've picked 5, A1 through A5. So I've selected number of modes equal to 5. And here, right here, is where I set up my neural network architecture to learn my coefficients a sub n as some function of time. I'm first defining the number of layers. So I've picked the same number of layers and nodes from the black box example. I have 2 layers, each with 50 nodes. I'm using a transfer function called a tanh. Let's not worry about that. It's a nonlinear conversion from the inputs to the outputs of all the nodes. Again, the stuff inside of here is the black box component, that block that just maps a list of numbers to another list of numbers. In our case, it's going to map position and time to the coefficients a sub n. Okay, and throughout my code in MATLAB, you're going to see this kind of language called DL and then something, DL array. DL stands for deep learning. It's just MATLAB's way of structuring their information. So don't worry so much about this DL thing. It's just MATLAB converting a list of numbers into something that it can take in its neural network built-in functions. So here's where we specify the number of training loops and how much iterations we're going to do, how fast it's going to go through gradient descent, etc. Again, the details of the actual convergence of the training. And then here is the main workhorse of how we're structuring everything. So for number of iterations going through a training loop, over here I drew this blue circle kind of going back and forth, back and forth. That's the number of training cycles it's going to do. And with this line right here, it's taking this function called model loss and inputting position, time, thermal diffusivity, the true temperature data, so that's your data matrix, and DLnet and DLT, again, is just the formatted version of DLnet is just the formatted version of the neural network black box nodes and layers and how they're connected. DLT is an array of time points that the MATLAB built-in function can read. So don't worry so much about that. DLT is just the list of time points. DLNet is the actual details of the black box neural network. But I did want to show you model loss. Let's go to that. Let's open model loss. That's down here. So this is what that line is calling. It's model loss. It takes in the actual neural networks. It's taking in time points, diffusivity, and the actual temperature measurements. So first, what it's doing is forward is it is taking the neural network, the black box neural net. It's saying, okay, at that time point, predict for me what my coefficients are. So A sub prediction, so PRED prediction, that contains my A sub n as some function of time. So if we look up here, that's the whole point. We modeled this forcing function where the coefficients A of n is some function of time. This is the thing that this neural net block is outputting, right? A1 through A5. That's why it's only a function of time. You notice that we're feeding in time points. So what this line is doing is it's saying, take my neural network at that time point, evaluate at that time what my coefficients are. That's exactly what we drew on this architecture diagram. So it's taking its current iteration's predictions of those coefficients. And then here we're just defining the length of the time points, the spatial coordinates, taking a small little increment, that's dt, so that's like the increment, the discretization in time. And modes, of course, is 5 in this particular case because we're taking 5 modes. It's taking that prediction of the coefficients A, and it's putting it into this loop inside of here. So a lot going on here. Let me go through this. First, we're having a for loop where the index t sub I is going from 1 to the total number of time points. So that's saying I'm going to go from 0 times, as my first index, time t equals 0, all the way to tf. Okay? And I have an inner for loop that goes from number of indices or modes, 1 going to n modes, which is 5 in this particular case. All right, so this first term right here is decay. This is equal to exponential of negative alpha, my thermal diffusivity, times eigenvalues n pi squared times t evaluated at that time, ti, minus the other time point t going from 1 to ti. Now, let's go back up to the board. That is precisely the integrand. I hope you see that. So on the screen, there's an exponential right there. Okay, that's an exponential right there. Exponential of negative, I have alpha times n pi squared times t minus tau. This is t, that is tau. Remember, we're integrating over tau. So that's why this t is going from 1 to t sub I, because you're integrating, you're sliding that tau from 0 to t. It's sliding all the way from time t equals 0, so the index of 1 is 0, all the way to current time t. This is sliding, that's tau. This is just t, that's the current time. Now we're taking that exponential, and that's decay. And look, we're multiplying that decay with our predicted values of the coefficients. So this is a sub n of the mode from going from n of 1 to 5 of the time points 1 to t sub I. Because what we're doing is we're trying to integrate this thing. We're slapping on this a sub n of tau, multiplying with this exponential, and look, we're finally multiplying by a dt. That's the small increment d tau inside this integral. This is just the trapezoid rule, right? When you take an area under the curve, which is what we're doing here, everything in blue that I've shown you up on the board, this is an integral. If you want to numerically integrate this, you just use the trapezoid rule. You get the height, you multiply the width. That's exactly what we're doing here. So conv underscore sum is the integral under the curve, everything in blue right here. And now we're taking that thing and we're multiplying it with sine n pi x. So everything here That is right here. Okay? Area under the curve times sine n pi x. Exactly what we have on the board, translated into code. And finally, we're just going to add those values over the different modes at different time points. You have a temperature prediction at current time that's added to everything I just mentioned, and it just updates. So that's where the summation happens. And if you saw my lectures with the Fourier series, separation of variables, the code looks very similar, right? We're evaluating orthogonality, we get the coefficients, boom, you put the coefficients inside of a summation, you get a for loop, it's identical. So this code should look very familiar to you with a minor detail here and there. And the main difference is we're now obtaining the coefficients through the black box output of the neural network. Now, what we have is this temperature as some function of position and time now, because the position came for free from the sine n pi x. So now we're going to take that prediction. And again, you can see here that it goes through a MATLAB language conversion. So it's taking the raw values of time, temperature, prediction, DL, deep learning array, so it's converting that vector into something that MATLAB can learn in its built-in deep learning function. It's converting this. It's also converting the data set that you fed in, your experimental measurements. So now we're going to compare these two quantities. Boom, right there. So that is our loss. Back on the board, right here. T prediction minus T true. That's your experimental data. Squared, that's our loss. So you can see right here we have our loss as the average of all the points inside that space squared. And based on that loss, we're going to calculate what's called gradient descent to figure out how should we adjust the new parameters inside our neural network, because the loss for early iterations is going to be very large, because the true answer is going to be very different from the predicted temperature. So we need to iterate. And therefore, it's going to spit out this quantity called gradients, which is one of the outputs of this model loss function. So now if we go back up to the main loop up here, so we were here earlier. So this gradient is now the output of the result of the process I just explained. So this function at model loss has all the structured model, all the physics insight we put in, it solved it. It's now going to spit out this gradients output. And now this is where we update the network to do the training. Now we're at the training step right here. Now we're calculating the loss. It's going to go back up into the neural network so they can spit out a new set of coefficients a sub n that is hopefully closer to an answer. So now what we're going to do here is we're going to do gradient descent using this code in here, the MATLAB built-in function called adaptive moment estimation, ADAM. So it's ADAM update to update the weights of the neural network. So that's what this built-in function is doing. It's taking in the neural network architecture, it's taking the gradients, a bunch of other details, kind of options for this built-in function, and out comes a new DLnet. So DLnet is this guy right here. Let me just write that down so that we're absolutely clear. So in my code, DLnet is this block right here. You just saw me calculate the loss using a given guess for my coefficients. Now it's here, it calculated loss, it's calculating gradient descent. Boom, it's going to feed back into DLnet, and that's how it's updating all the parameters, and it knows how should it change the neural network parameters such that I am closer to minimizing this overall loss. That's what this is doing. Pretty cool. Okay, so now it's updating this neural network, and then it's just looping. So that the rest here is just, trying to get the output, track the loss, some displays. Let's not worry so much about that. But the point is now it's going to loop and go to the next iterations. Now epoch is now going from 1 all the way to maximum, which we set to 2000, but it's just entered a new loop. So it just keeps doing this over and over and over until this network, DLnet, tries to minimize the actual result of that temperature with our given data. And it is actually solving our PDE. And that's why it's nice. I put a little comment here saying, what's really nice about this structured model is it is guaranteed to solve the heat equation. Yeah, duh, because we just solved the heat equation and we're putting in that structured model into our neural network. So what's really cool about this is whatever the neural network does, it is always going to be slaved by this equation. It can never deviate from this. And this equation solves the heat equation. So it's never going to deviate from that. Again, remember that universe? We're shrinking it down. It's shrinking down to that small little space because whatever it does can't escape that confined boundary because you confined it to that boundary. So it's going to do everything it can inside that small little space in the universe to find the right combination of A's such that this is minimized. That's what it's doing. Okay. Let's evaluate this and see what happens. All right. So it's doing it. It is solving the partial differential equation over and over and over again using our separation of variables. It's trying to minimize this loss. And all the stuff down here, again, like I said, it's just outputting in the command window the number of iterations it's gone through and the loss. I'll just keep this display on the screen so you can see how the error, hopefully, will go down as a function of iteration number. Okay, it looks like I went through the training process. So now let's look at the training loss. What I'm plotting here is the mean squared error, the loss of the model temperature from the true temperature value. And you can see it's very high initially, and it goes back down, 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 down. And then it gets better and better as the more iterations we do. So it's training to a better and better converged value where the model temperature profile is agreeing more closely with the simulated true answer for the temperature. You can see every once in a while it jumps because the model is somehow searching a different space. All of a sudden it gets all of it bigger. Actually, at the very end of our iteration, it looks like it's jumping up. So I'm a little bit concerned about what the temperature looks like. So let's see what it's doing here. Okay, so now what I'm plotting here is the temperature profile shown on the y-axis as a function of the position x. Okay, shown right here. So that was kind of interesting. Let's play that again. So the red curve right here is the gray box model like I've shown, and the dashed black line is the true data set that you've provided once more. So you can see the agreement is pretty good until close towards the end of the cycle, it's not doing as well. I'm gonna get to that a little bit, but I also found it kind of interesting that I think right now we just happen to end the training cycle just where it kicked to another space. So let me just try re-evaluating this for a smaller number of iteration cycles because every once in a while, like I said, the error jumps up. So let me just rerun this again, this time changing this to a smaller cycle. And it kind of looks like, based on this history, it looks like even around training of 800 or so, it's pretty good. So let me just shrink that back to 800. And actually, you're seeing this in real time. This is the kind of consideration you have to make when you're developing these type of models. How much do you train? What's your learning rate? Things like that. Those kind of have to be trial and error. So based on that trial, I found that every once in a while, the error spikes up because it sometimes blasts the neural network into a completely wrong territory and it's iterating. So let me just shrink this iteration back down to 800. Let's just see what happens. Okay, so now it's done training for 800 cycles. Let's plot the error. Okay, so again, it's shrinking lower and lower as more iteration count goes on. It looks like it's smoother this time. So this is where some of the stochasticity may come into play in the training cycle. So let's compare the temperature profile once again. I'm just plotting here. Okay, so the red is the neural network model, and the dashed black line is the true data. You can see it's performing better. Let me just play that again. Okay, so that was a little bit better because I think I just ended that iteration cycle on a place where it converged to a little bit better value. Okay, so that is a demonstration of this structured model on this particular forcing function in a situation where we have cosine 2 pi t times sine pi x. So what we can do is to actually check our answer, because in our particular situation, we know what the final answer is. What I'm showing you here is the actual output of the neural network. So in our structured model, the neural network is spitting out A1 through A5, right? Those are the separate modes. That's what's shown here. So I specified A1 through A5. Those are the 5 degrees of freedom the neural network has. You can see that it only has one dominant mode. So this blue curve corresponds to A sub 1. And so back on the board, A sub 1 would correspond to A1 of t, so that's sine pi x. You would expect that to be the dominant mode because the real answer is sine of 1 pi x. So it's the only mode that actually was contained in the original answer that we generated. So we, of course, this forcing function, we put that in there and generate the data, right? But this actual gray box didn't know that we put that in there. It found the coefficients, and we're now checking. We're now checking the answer to see if it's consistent. What we see is that A1, right, looks like that. That's our mode. And then every other mode, A2 to A5, is just straight line right at 0. The only reason why you don't see the other colors is because they're all right on top of each other. They're all equal to 0. So red, orange, purple, green, they're all smack on top of each other, very, very close to 0. So essentially what it's saying is a neural network, even though we gave it 5 degrees of freedom, A1 through A5, it's converged to only a single value. And it said, actually, we found that based on your data, you actually only need 1. Which is the right answer, which is great, right? It's found even through all this process, and you gave it more degrees of freedom than it needs to have, it converged and said, oh, I only actually need A1 of t, which is correct because that's the model that we put in. Okay, so now let's look a little bit more carefully. So this case 1, the coefficient is right here. This is A1. That's A1 because that's A1 sine of 1 pi x. Therefore, this A1 under the hood should be cosine of 2 pi t. So now if you go back to the figure here, you can see that the initial part is a little bit off, but yeah, more or less, this oscillation looks a little bit like cosine. And you can see that at the end, it's a little bit off. And I'm going to show you, it's very fascinating. This is the kind of thing where I'm discovering new things about this area that's very, very cool. So I'm going to explain why it does poorly near the end. And I'm actually going to do that for case number 2 because I think it's going to be more obvious for that particular case. So overall, it's giving kind of the right answer. It's saying, oh, I only need 1 mode, and it looks kind of like a cosine 2 pi t. Great. So now I can also animate the forcing function. This is the f of t. So this is not the full temperature profile, but I'm just plotting the function f of t, which is the actual model we put in here in dashed black line. What I'm plotting here in dashed black line is literally just cosine of 2 pi t times sine pi x. I'm plotting f of x as a function of x. You can see it goes up and down because it's following cosine 2 pi t, up and down. So I'm going to just play that again. So the red curve is what we're predicting, what the neural network said it was based upon A1, A2, A3, A4, A5 times the respective sine n pi x. That's the red curve. And yeah, for the most part, it does okay. There are some deviations here and there, but for the most part, it's doing okay. A couple of things I wanted to mention. First of all, you now have a model that you can use, right? We now have the coefficients A1 through A5. In this particular case, you only needed A1, but you now have that. You have A1 through A5. You have this integral. You have numbers. They're physical numbers, right? I mean, at the end, we have this. So here, we have a matrix of the A sub n's. So this right here, this row just corresponds to, let me just plot this just to show you. That row corresponds to A1 as some function of time. That's what I just showed you. And everything else is very close to 0. So like that one, yeah, 10 to the minus 4. So this is basically a flat line at 0. So what you have at the end of the day is a list of numbers in time that will help you evaluate this model. So you have a model that you can use. You can differentiate this. You can take this to make predictions about temperatures. You can actually do stuff and play with it, right? Compare that with the fully black box model. You just got a table of numbers. Your neural network is just numbers in, numbers out. You can't really do much with it. You can't differentiate it. You can't predict, extrapolate outside. With this, you can do a lot more. So this is the main advantage of a physics-informed or gray box model, because you can actually interpret what's happening. The interpretability is one of the key advantages of this gray box model. So it's kind of like saying we humans did like 90% of the work because we did a lot of work to get to this form. But the 10%, the really annoying part where we don't know what the coefficients are, we relied on the computer to do it for us. So the 10% part, we did use data-driven to find what that was, but ultimately most of the work was done by a human. So this is what I would call using ML as a calculator. This is what I often say is, when you're solving arithmetic problems, you do most of the work, but at the very end, you have an annoying product that you have to figure out. You just use a little calculator to figure out what that product of a 3-digit number times a 4-digit number is. You're using a calculator because you could do a 3-digit number times a 4-digit number, but that's really annoying for a human to do. So we're going to use a calculator to do that. Same analogy here. Most of the work we did, but this part, a sub n, is really annoying. I don't want to figure out what that is. Let's just use ML as a calculator to figure out what that is. So using ML as a calculator, where most of this is human-derived or physics-derived. Okay, let's move on to another example, because you might be saying, well, yeah, I kind of expected this model to do pretty well because you're putting in a sine series as your model basis function, and the simulated data has a separable form, some function of time, some function of x, and it's got a sine pi x in it. Of course it's going to agree. Well, let me make this a little bit harder. It's still going to be easy, and then case 3 will be even harder, and a lot of interesting things happen. So let me just go to case 2 and then give you some insights based on what we learned from that case. All right, this is our next example, case 2, where now our real forcing function has 2 modes present. We have the same modes present from the case 1, but we've added another mode. Now this is 1/2 sine of 3 pi t sine 2 pi x. So we've taken a superposition of 2 separate modes in position and in time. You might still think, well, that's not conceptually much different because you're still just putting another superposition of another sign, and of course you're going to get the right answer. I get you. I get what you're saying. But let's just check this out because it's sometimes good to take baby steps. And I wanted to point out one specific feature that you get when you add this term and make it slightly more complex. Let's try out this term. So moving over to the screen, let's go up here, and I'm going to expand this guy. And so here is our 2-mode example. So here you can tell that I'm putting in this function, right, which is what I just explained. So this data set contains the temperature data that was solved from this function under the hood. Again, the neural network in the gray box does not know where it came from. It does not see this actual forcing function. So let's evaluate this. I'm actually going to raise this again to 2000 because I think better training is just going to be better. So just evaluate that. Again, using 5 modes. Let's see what this gives us. This is going to take a little bit of time, so I'm just going to fast forward through this training process. Okay. All right, it is now done, so let's take a look. First at the loss. It's going down, down, down. Every once in a while it spikes. Oh, it looks like it spiked again. This always seems to happen. Let's just take a look anyway to see how it looks. And then here's our temperature profile. So now T plot on the y-axis as function of x. Oh, it's pretty good. That's pretty good. Okay. That's pretty good. Okay, a little bit of wobble, but then that's not so bad. Okay, so near the final time point, it's pretty bad. Okay, let's play that again. So the red is the gray box, the dashed black line is the true answer, plotted between 0 and 1 in space for different time points. So you're seeing the actual temperature profile inside your material as a function of position and time. Let's play that again. Once more. So it's got 2 modes this time. So now you can see the temperature goes up in one space, goes back down in the other space, and it's not symmetric at the origin and at the half space anymore. So it goes up and down, up and down. Good. And so what I want, one more thing I want you to take a notice. Notice that at early times, it's pretty good, right? The model does a very good approximating the actual solution. And then towards later in time, it starts to break down a little bit. And at the very end, it's pretty wrong, right? We're gonna talk about that. That's actually a pretty interesting effect that I'll get to in a little bit. But for now, let's keep going and look at the coefficients. Boom, here they are. So once again, I fed it 5 modes, A1 through A5. But like I said, in case number 2 up here on the board, we actually only have 2 modes, mode of n of 1, n of 2. One of them should be cosine 2 pi t. The other one should be sine of 3 pi t divided by 2. So this one is A1 of t. This one should be, ideally, if our model has converged properly, this should be A1 of t, this should be A2 of t. So let's take a look. First of all, we find that A3 from A3, A4, A5 is all equal to 0, roughly equal to 0, so that's good. There's a little bit of A3 at the end. Again, ooh, interesting, right? It's 0, 0, 0, and then at the end, it starts to trail off. Again, we'll talk about that. All right, A1, so this is supposed to be cosine 2 pi t. Yeah, pretty good until the very end where it diverges. Again, same result that I'll talk about a little bit. And then A2, which is shown in orange, is supposed to look like sine 3 pi t. So, okay, so yeah, that kind of looks like sine 3 pi t, right? That's sine 3 pi t divided by 2. So the magnitude should be between 0.5 and negative 0.5. So yeah, it's roughly hitting the boundary. I mean, this kind of looks like a sine 3 pi t magnitude 1/2. Yeah, so that's pretty reasonable. So good. So overall, you know, it's actually finding the right coefficients through this gray box model. Okay, so let's look at the actual forcing function. Let's compare our final answer for f. So dashed black line is our solution for f. Okay, and then the red line is the predicted value. Yeah, it's a little bit off, a little bit off, a little bit off. And at the very end, whoa, very off. Okay, very off. Let's play that again. So this is, again, the forcing function itself. Dashed black line is what we inputted to find our temperature profile. The red line is what we found from the neural network. Coefficients A1 through A5 times sine n pi x. So you can see it did okay throughout the entire duration of the simulation until the very, very end where it diverged. Okay, so let me talk about this very interesting. So first of all, it's pretty decent, right? I mean, some of you might criticize and say, oh, well, the black box seemed to do a lot better. I mean, the black box was spot on, and this one is not as good. Even case 1 was a little bit deviating. Yeah, that's actually pretty common. That's expected because the black box is optimizing every parameter inside the entire universe, making everything match and driving the mean squared error all the way down to 0. Right. But you just have a table of numbers that's uninterpretable. It's just interpolating between those points. So of course it's going to match very well. The whole purpose of developing a gray box model is to have an interpretable, ideally transferable model. It's not going to be perfect because we structured it in such a way that the machine learning has less degrees of freedom. It doesn't have the entire universe to optimize. It only has that small little disk. So it's optimizing over that little disk with your given data input. So of course, it's probably not going to interpolate as nicely as your black box model, but that's not the point. The point is that it is an adequate model for whatever you need in your research application. And the key is that it's interpretable. You can do stuff with it. You can differentiate it. You can predict material. You can do stuff, right? You have a formula. You have a formula that we wrote down in pen and paper. It's interpretable. That's the main thing. Okay, so back to this issue of why is it deviating towards the end of the cycle? Let's talk about that now. So let's talk a little bit about what you saw. In both cases, you saw that it was pretty good in the early to middle parts of the solution comparison, but near the end, it just kind of took off and became very unreliable. So why the disagreement near the end of time? Well, let's go back to our solution because this is actually a pretty interesting reason why. So if you look at the solution that you have in your gray box model, the coefficients a sub n is evaluated at some time tau. And you're going to integrate this coefficient from 0 to time t. What this means is that for a given value of your coefficient A at a particular value t, it is predicting a future value of your temperature, right? Because for a given value tau, you're going to integrate from 0 to t, the temperature that you want at some time t. It's using past values of A, okay? But a particular value of A is predicting the future, but not the past. Let me just graphically illustrate this so that's a little bit more easy to explain. All right, let me just try to explain that a little bit better because I think that was a little bit confusing. So let's suppose we have our coefficient A sub n as a function of tau, and one of them looks like the following. So let's say that I want the temperature at a particular time point. Let's just say at time t equal to 1, which might be, for example, here. So if I were to evaluate the temperature at time t equal to 1, what this is doing is that now my upper bound, my integral, is going to be time t equal to 1, because that's the point where I want the temperature. So I'm going to integrate this thing from 0 to 1. What this means is that all values of A sub n beyond t of 1 does not matter, right? So for example, this point all the way over here might be A evaluated at time t equal to 5, a future time. 5 is bigger than 1. It's a future time point. But notice that A at 5 does not impact the temperature profile at time t equal to 1. It can't, because we're integrating from 0 to 1. It never hits tau of 5. You never integrate to that domain. Here, we're only integrating over this space right here. So my temperature at time t equal to 1 depends on the past values of A. So it's essentially taking an area under the curve. That's what we're doing, right? We're taking an area under the curve. So we're integrating morally. We're integrating this section, and this hashed out area will determine my temperature at that particular time t equal to 1. So it's a accumulated integral under the curve of A's that dictate my final temperature. And now you're comparing that temperature with the true solution. What this means is that your neural network prediction of A is going to be really good earlier in your solution because it's got all this future time that it is iterating and correcting and optimizing over. So it's got all this future data that A depends on. So for example, a particular value over here, this point, which might be AN at 2, as an example, this value of A2 will impact all the temperature profile from 2 all the way to TF. That means that it's going to get a lot of practice. A of 2 or A of 1 will get a lot of training, a lot of practice to optimize over the entire future trajectory of your temperature profile. That means that these values earlier in time is going to get a lot more iteration, a lot more training, a lot more practice, such that my temperature over the entire duration of 0 to TF over here will ultimately be optimized. In contrast, the values of AN, very close to my final time point, TF, doesn't have a lot of future to look forward to. It's only seeing a real-time data very close to the end of the temperature, and it's only comparing the error at the very end. So it doesn't have future data of temperature to iterate and improve the value close to the final part of the cycle of close to TF. So what it means is that everything over here is going to be very good. But when I get close to here, close to the end of the training cycle, in a way, this A can do pretty wild things and still get by with it. Suppose that my AN at the very end decided to do something weird like take off, which is kind of what you saw. In the video for AN, you saw that the AN was taking off. Right? Let me just plot that again just to show you. So here is AN. Look, so everything here has looked pretty good, and then both my orange and blue curve, which is A1 and A2, are just taking off. they're taking off. So at the very end, close to TF, again, back on the board, close to TF, you can see that it's just taking off, but that's not a big deal from the perspective of temperature minimization, because look at the error. The error is just a small little area. This hashed small little area in blue is the small bit of error that you're accumulating through this integral. So it's an integrated error. And I don't care from the perspective of the computer. It's saying, I don't care like what I'm doing at the very end. Hey, look, I'm still minimizing temperature over the whole domain because my tail can wiggle around a little bit here and there, and it's just not going to accumulate that much error. And that is the reason why in both examples I showed you, near the end, it performs very poorly because it doesn't have a lot of future data to train on. This is very interesting. I found this kind of consideration so interesting because it combined our structured model, because the physics, because we put that into the model. We put that physics there. We said, oh, A is going to get integrated over time. And the machine said, oh, great. I'm just going to minimize the temperature. I don't care what A does. At the very end, we put that structure in there. So it's kind of our, I don't want to say our fault, but it's by design that it's producing what we put it in, right? It's searching over that small little space, that small little disk inside the universe. It's producing that. Okay, so let's just show that F curve once again. So I'm just going to show you here that, again, it's pretty good throughout kind of the bulk of the simulation, right? There's a little bit of error, but not a big deal. But near the end, that's when it really takes off and is very wrong. It's not even close at the very end, right? And we know why. Now, by the way, if you wanted your answer close to the end of the time cycle to be very accurate, let's suppose your temperature, you want it to be very accurate near the end of the time cycle, you can definitely do that. There are a couple of different remedies you can do. The first and easiest thing you can do is to just collect more time points. Because I just showed you that a particular coefficient a sub n at some particular time t is actually going to improve with more temperature data into the future. And the more future data you have, the past values of A get better and better. So the easiest thing is, if you're able to, just collect more data this way, such that your data matrix of temperature through time and position just becomes longer downwards. Because then you have a couple of extra pieces of data down here beyond TF that then will allow you to model past that point. And thereby, now you're going to have this section become more and more accurate because it's going to be predicting temperatures into the future. Now, that's one way to make the end of your time cycle more accurate in your modeling. That's kind of a brute force way of doing it. Well, there is a slightly different way of doing it that doesn't involve incorporating more data or measuring more data. What you can do is to change your loss function. So the way we've structured it here is you're taking the temperature across the whole domain from time t equals 0 all the way to TF, and you're taking the true data that you fed in, and you're minimizing that error across the entire range. What you can do is to bias and preferentially say, oh, ML, I want you to minimize the error more preferentially near the end of the cycle, because I know that my gray box is going to be the weakest near the end of the cycle. So can you place a little bit more weight and a little bit more preference and bias near the end of my time? You can definitely do that. You can add another term into here, or you can actually change the structure of this harmonic itself so that you're making a gradient of penalty as you move forward in time. There's a couple of tricks you can play. You can add this to another term and say, I'm going to penalize the boundary value at the end of my cycle more heavily. I'm going to put a prefactor out in front and penalize that more heavily. So there are a couple of things you can do to massage your loss function and structure it in such a way that you penalize more heavily near the end of your cycle to make that temperature more accurate. Then if you do that, presumably your coefficients a sub n of time t will be accurate more close to the end of the cycle. All right, that was a short little aside on how you could actually improve the entire duration of your modeling until the end by changing your loss or collecting more data. All right, So far so good. But you're probably saying, okay, well, both cases, I kind of expect the structured model to do pretty well because you're giving it easy case examples. You're giving it examples where it's just an expansion of signs and your actual model basis function was also an expansion of signs. So yeah, I kind of expect you to do pretty well. Let me give you a case 3, which breaks some of that easiness that you might be suspecting. Let's consider this example as case number 3. The function that generated temperature data is sine of the argument 2 pi t, the time, plus pi x, plus sine of the argument negative pi times t plus 2 pi x. Now, the key difference is that unlike before, where the function of time and the function of x were a product of each other, now it's the argument inside the same sine function. So we have sine of the argument of 2 pi t plus pi x. Now, we've really broken it because this can no longer be written as a separable form. I cannot write this as some function of t and some function of x, the product of each other. So the key thing is that the forcing function is not separable. I can't write this forcing function as some function of time times some function of x, because that's what we assumed over here. Our model, our guess for the forcing function was expanded as a basis function. We have some function of time times some function of x. So we assumed a separable form. The actual under the hood true forcing function is not separable. Now what happens? Let's try it out and see what the gray box tells us. So I'm going to go back into the code. We're here. I'm going to call this cross mode. It's the non-separable time and position following this forcing function. Again, I've solved the PDE, put the data inside this data matrix. I'm going to evaluate this. But before that, I'm going to change a couple of things. First, I'm going to make it have a little bit more degrees of freedom by giving it 10 Fourier modes. Instead of just 5, I'm going to give it 10 modes. It's got a little bit more flexibility to adjust, more modes, more Fourier series. And otherwise, I'm just going to run it. OK, that's the only change I'm making. Otherwise, I'm just going to run it. And once again, this is going to take a little bit of time, so I'm going to fast forward through this section. OK, it looks like it's finished running, so let's look at the result. First, let's look at the error as usual. Go down, evaluate the error. It looks something like this. OK, so it's going down, down, down. It spikes every once in a while, like we've been saying. Every once in a while, it escapes its local minima. It goes to a crazy place, and then it goes back down again. It looks like we've ended at a good point there. OK, so moment of truth. We're going to compare the temperature profile from the true data to our model. Let's check it out. Here it is. Oh, it's a beauty. Oh my gosh. I gotta watch that again. that was amazing. Let's look at this again. Oh, that is pretty insane how good that is. Wow. Once more, I think I could just like permanently loop this, and I might just do this for the rest of my day just to admire this. That is pretty good. Holy smokes. This is the temperature profile. This is what you've measured in your thermocouple inside your material. Wow. As a function of position, the temperature is pretty well captured. Even that weird lobe. I mean, look what's happening at the boundaries. It's whipping at this point, right? Look, it's going up, 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 up there, and then it whips down and even capture that pretty steep gradient there. That's pretty good. Whoa, okay. And by the way, if you're wondering why did case 1 and case 2 not look as good, that's kind of the details of the optimization. I'm pretty confident that if we tuned a couple of parameters here and there, the iteration, the learning rate here and there, it will look as good as the one that I just showed you. It just so happened that my particular combination of parameters was good and we ended at the right training cycle such that we had a really good result at the end. It's the same with case 1 and 2. The point of today's lecture is not so much to actually show you great agreement on this fake data. It's to show you the concepts, right? So if you're skeptical of case 1 and case 2, that was also equally going to be good if we played around with it a little bit more. This is just kind of a first cut of what I just wrote up. So the reason why this is so good, does that surprise you a little bit? I mean, you just saw how good that was, but wait a minute. How can that be possible? We put in a forcing function under the hood that's not separable. This thing right here is not true, but our model that we used in the structure assumed a separable form of time and position. But in reality, it's not that. And it might seem strange to you that it's such a good agreement. I mean, how can that be, you might wonder, right? You know, I have this equation, I have this forcing function. If that forcing function is really wrong, which it is for our case, because look, our f, I'm going to show you the f, it's going to be really, really wrong, right? I mean, look, it doesn't even look the same. I mean, it's just, you can't write it in a separable form up here, but we assumed a separable form. Then why is it then that we have a very wrong f, but yet our final temperature, as you saw, was super compelling? Let's dig in here for a little bit. Okay, first, I want to show you the Fourier coefficient modes that we learned at the end of this training. Now, this time, like I said, the one change I made was I put in 10 Fourier modes. Right here, we have all those 10 modes, A1 all the way to A10. So this is activating sine 1 pi x all the way to sine 10 pi x. It's putting 10 frequencies in there. And you can see in the previous examples, we only had A1 or A2 that was activated, and everything else was straight all the way at 0. In this particular case, what we find is that every single mode is activated. A1 shown in blue, A2 shown in orange, all of it. You can see every single mode has been triggered as a function of time. It's non-zero, which means that going back up to the board, it's saying, I'm going to take the summation from 0 to 10. I need all 10 of those. I need every single one. If I lose one and keep everything else the way they are, it's going to be very wrong. It's saying I'm going to keep all 10 modes. So when you think about what's happened, is this neural network block compensated for my wrong Fourier assumption of the forcing by using all degrees of freedom, all 10 of them, to make it so that we minimize the temperature loss, the data loss at the end. So this is a really interesting thought, that I put in a wrong model for the forcing function. Very wrong. But it figured out a way to compensate for my wrongness and used everything it can to wiggle around to make sure that at the very end, my temperature agrees with the data. Okay, that's what it has done. So let's move on, and I want to show you the actual forcing function. Here, the forcing function, f. I'm plotting f on the y-axis as a function of position x right here. Black dashed line is the true answer. The red curve is the predicted value of f based upon this Fourier sine expansion using A1 through A10. Let me just play that again. It is very, very wrong. I mean, look at this. It's not even close. It's going way above and way below. It's wrong even at early times. And there's one thing I really want you to look at, and that is the value that's happening at the boundaries. So there's actually two things that are very wrong about our assumed form of f compared to the actual forcing function f. Up here, I just showed you that it was non-separable, but it's more than that. Look at the boundary values. When x is equal to 0, sine 2 pi t, that means that the boundary is going to lift off from 0. Same at the end. At x equal to 1, usually sine of 2 pi and sine of pi is 0, so it's pinned at 0. But now, because there is an argument of time inside the argument, the boundary values are lifting off. Let me just play that once more. Okay, again, you can see the boundary value lifts off. Look, it goes away from 0. Look all the way down here. It goes down to almost to -2 at the boundary, and it goes back up. Whereas if you look at my model, red, it's always pinned at 0 at both boundaries. Look at that. So the boundary values are incredibly wrong, right? Right there, that's so wrong. The black and the red curves are very wrong at the boundaries, okay? So again, what it's doing is we constrained the model to take on a very wrong form. So it's doing everything it can do inside the domain to compensate for the wrongness at the boundary. That's why in the interior of the curve, it's wrong. It's deviating from the true forcing, because if it can't get the boundary correct, it needs to do something else inside the interior of the boundary to make it and compensate for the wrongness at the boundary. And therefore, everything has to change. So here's a super, super important point that I wanted to make. Just because you have an agreeing temperature profile does not mean that your forcing also agrees. You just saw that. I mean, look at how good this actual temperature agrees. Look at this curve right here. This is the temperature profile. That is immaculate. And look under the hood. This is the forcing function that we put in. Terrible. Terrible. So how could it be that we have two very different forcing functions that ultimately gave us the same correct answer? Let's think about this for a little bit. I wanted to discuss the concept, an important concept of uniqueness of models that we develop. Let's think about this, because it seems like we just produced two different functions f, but ultimately got the same answer for the temperature profile, right? The true f and my f were very different, but yet the final temperature agreed very well. So are models not unique? Fundamentally, we are integrating our forcing function. We have a differential equation. Yeah, there are integrations happening. On a broad picture, when you look at this equation, yeah, you're integrating on some form or another. So you take this forcing function and you're integrating it at some level. Let me ask you a question. If I were to ask you to draw me some function where the area under the curve between 0 and 1 was equal to some fixed value, say area of 1, can you draw that function for me? Let's actually do that together. All right, I'm going to draw a function between 0 and 1 where the area under the curve is equal to 1. Just a square. I have height of 1 all the way across to the position x of 1. The area under that curve is equal to 1. Well, someone else might say, oh, I can draw a different function also with the area of 1. Here what I've done is to draw a rectangle with height equal to 2 that goes only half the distance to 0.5, goes down to 0, and then stays at 0 all the way. So the area under the curve of this rectangle is also equal to 1. Well, you can get the point here. I can draw any number of curves. I can draw a parabola. Area under that parabola is equal to 1. Some of you might say, oh, I'm going to have a curve that goes negative. That's no problem. You can have a curve that goes negative like that. And the area under the curve of the negative will cancel the positive such that the positive area will give me an area of 1. So you can see that there are an infinite number of ways where I can draw some function where I take the area under the curve is equal to 1. That's what's happening here. I can come up with any function f. Well, not any function, but there are many, many different versions of f where after you integrate it, at the end of the day, you come up with a temperature profile that agrees with each other. That's what's happening. Therefore, what my solution is doing is because I gave it the wrong model for the forcing, it's pinning it to be 0 at both ends, and the A sub t is doing everything it can. It's taking all 10 degrees of freedom, doing everything it can to make sure that my model T agrees with the simulated true temperature profile. And you saw that when I plotted the forcing function. When I plotted the forcing function f x comma t, the actual real answer had boundaries that were offset away from 0. It lifted off away from the origin, but because my model constrained it to be fixed at the origin, it was bound to sit between there and there, and therefore it had to do all 10 modes and go crazy. It had to do everything along the way to compensate for the fact that I have errors at the boundaries here and here. So it's doing stuff over here to compensate for the wrongness of the model I put in. And here we get to an important philosophical point about developing a model. Just because you have cooked up a model that happens to agree with your experimental data, it does not mean that your theory is correct. We were wrong. We cooked up a model, said our forcing function must be a basis set, expanded upon signs. We found all 4 or all 10 Fourier coefficients using the gray box model. It agreed. And in this particular toy example, we actually knew under the hood that this was the actual solution. But in a real research setting, you don't know what this is. You can't check your answers. There's no control like the one we've done where you can say, oh yeah, it's agreeing, under the hood it's agreeing. You don't have that. Out in the wild, out in there in the scientific wild, you don't have any idea whether the model you cooked up is actually correct. And so a lot of scientists and engineers and researchers out there are collecting all sorts of wild experimental data, which are correct and good. So data are king. So the experimental results you got are likely correct. I mean, it most likely could be correct, unless you're making some crazy artifact in your microscopy or system preparation or whatever, right? Barring those crazy artifacts, it's likely, it's got all the physics, chemistry, biology in it. But when it comes to developing a model for that data, you need to be really careful. People come up with all sorts of models that seem to agree with the experimental data points and claim that they have a theory and a model that, explains all of that system or material. That's not necessarily true. I just showed you case in point, an example where that's not true. You can have all sorts of different models that produce the same integrated area under the curve morally, right? And therefore, it doesn't mean that your theory is necessarily correct. So that's where you have to be very, very careful. Careful for yourself when you use AI or data-driven methods in your own research. Be really careful about how you use it. But also, when you listen to someone else's research at a seminar or pick up a paper from a journal article, be skeptical about what they've actually done. Do you really believe their theory? Do you believe their model? Just because the curve agrees with the final output data? That's not necessarily true. It doesn't mean that the theory is correct. And this is where way back in part 1, I said, this discussion is going to get into kind of a philosophical point about modeling. Here it is. This is the philosophical point. But it still means that you have to be good about where your physical intuitions guide you. So, pinning ourselves to an actual physical system, you probably know some things about your polymer film or whatever material you just generated experimentally. You probably know some things about that, and you know some things about the electrical wire or the exothermic chemical reaction happening inside the material. And that will inform you on whether this is the correct guess to make. If you know that as a function of time, the forcing is going to lift off of 0 at the boundaries, then you probably wouldn't want to write it in this way, for example. Or if you know some insight about the particular forcing that you might have based on your physical intuition, being a chemist, biologist, or physicist, this is where it has to go in. But the danger of data-driven methods is that you might put in a model accidentally, and your neural network will do whatever you tell it to do. It will optimize, compensate for your errors, and seemingly give out an answer that is spot on. And that's where you have to be really careful. Your physical intuition will generally guide your design of a model. In this particular case, our physical intuition guided our model for the forcing function. So what we did was to say, in this entire universe of things that the data-driven approach, machine learning, could have searched, we said, oh, you don't need to look in this entire space. Please look here. Machine learning, please learn here. But it turned out under the hood that the true solution lied outside the circle. So what we inadvertently did was to constrain the machine learning to learn in a search space that the true solution for f, the forcing function, didn't even exist. And this can be a problem because, again, you don't have access to this forcing function in reality. So let's suppose you make some measurement of your temperature profile, you go through this gray box procedure, you assume a form of your basis function, you search the machine learning through here, and you say, wow, look at the temperature agrees so well. That means my f must agree with the actual physics of this electrical wire, the chemical reaction happening inside a material. I'm going to go off developing a nuclear reactor water jacket. No. That would be terrible, right? That would be a terrible idea, because if you try to transfer what you thought was the correct answer to another application, it's likely going to fail disastrously. And the transferability is going to be very poor if you assume incorrectly that you had the right model and the right theory, but all along, all it did was machine learning just tricked you into thinking that you had the right model, when in reality, it was just using all of its degrees of freedom and optimizing and outputted a forcing function that happened to be very wrong. Therefore, sometimes putting too much constraints or too much mathematical structure into your model could actually hurt you. So if we were to back off a little bit and say, oh, I'm not going to make the search space as narrow as confined. I'm actually going to broaden it a little bit more so that now it's searching here instead, then you have a better shot of actually capturing the true forcing function. So again, this is the interplay between how much physics and mathematical structure you put into your model that will make it smaller and smaller and smaller and smaller and smaller. And that point is the white box model. The point in space is the white box where you know every dependence of everything is a point. As you make it bigger and bigger and bigger, you approach the black box. So the grayness is how big that circle is and how much you constrain it. And if you constrain it too much, you're going to be away from your solution. So you want, sometimes if you don't know the chemistry, bio, or physics, you want to back off of it a little bit to allow the computer to search to the global minima, which might be your true solution. All right, so one final lesson. So if you have a model that's based on the correct theory, if such a thing can be developed for your system, i.e. the white box. If you know everything from first principles about your model, usually restricted to simple systems and toy problems, but if you have an exact correct theory, then the forward arrow should tell you that it should agree with your experimental data. But the backward arrow is not true, because if you have a model that agrees with your data, the agreeing with data could be coming from a number of different models. So I just want you to be really careful that just because a model agrees with some data, it doesn't mean it's the correct theory, because it could actually have come from a lot of different models, which is what you saw in this example. Okay, so one final thought. What this exercise taught me is that it's still critical to know physics, chemistry, and biology. I know there's a lot of hype and a lot of promise over machine learning and AI and data-driven methods, but ultimately, what I'm coming away from this simple toy example, by the way, this is a simple example in a real research application. It's far more complicated than this. But even for this toy simple problem, I'm seeing some little errors here and there creep up, and it just is not super compelling to me just quite yet to rely upon a computer and a purely data-driven method to develop good models. Physics, chemistry, and bio, actually, in fact, especially in today's era, we need more students, more researchers who are grounded in physics, chemistry, and biology, because it's so easy to produce models that seem to be correct, but actually not correct. And it's even more important so that we incorporate the right chemistry, physics, and biology into our models. With that thought, I will see you next time. Bye.